Okay, welcome everyone to lecture 22. Before I start the lecture and continue with a discussion of the eternal black hole, I wanted to address a question from yesterday, which I did answer, but perhaps I didn't answer very clearly. The question was, we discussed in the first part of this course many resolutions to other versions of the information paradox. So we discussed this principle of holography of information. We discussed the island proposal, the question is, for instance, the question specifically was about the island proposal. What does the island proposal, or what does the computation of the page curve tell us about the interior of these typical large states in ADS-CFT? So in particular, the question was, we could take the CFT, so the couple the CFT to a bath. Okay, so if we do that, even a large black hole will evaporate. And we expect to see a page curve. And the question is, what does this tell us about the interior? Does this shed any light on the puzzles we are discussing right now? The answer to this question, which I should emphasize, is the answer is nothing. Okay. The fact that you see a page curve on the boundary tells us nothing about whether the interior is smooth, or whether it has a firewall, or whether it has something else. This perhaps goes to emphasize something that we said several times in these lectures, that this page curve, you should really, if you really want to think about it precisely, there are many words that go along with it about, some information traveling from inside to outside, and we are collecting the Hawking radiation and so on. But really, the precise description, which also holds for the setup we have here, is that you should think of the whole setup from the non-gravitational point of view. So here we have an excited state in the CFT. This is, maybe this is like n equal to 4 Yang-Mills or something else. We couple it to a bath, which is a CFT d+1. And then, in this setup, so you make some interface. So you're just guaranteed that, you take an excited state and you put the bath in the vacuum. Energy will flow from this excited state into the bath, and you're just guaranteed that you will see a page curve. The fact that you see a page curve really tells you, it doesn't tell you that it doesn't even, you don't even require this excited CFTD to be holographic or to have a black hole in the bulk. You'll just always see a page curve. You have a tensor factor and you'll always see a page curve. So maybe one could ask a separate question. One could ask, if there was a firewall, how would the holographic entanglement entropy prescription reproduce the page curve, right? So that is a question we could ask. So the computations we did so far, they didn't in any very critical sense involve the interior, but they involve some properties of the interior. And so we could ask how this holographic entanglement entropy prescription would reproduce the page curve. In some cases, the answer seems, simple to understand. In some cases, for instance, in these eternal black holes coupled to baths, where we see the semi-page curve, you would probably just see a flat entanglement entropy kind of curve. But in general, the answer to this is we don't know. Okay? And the reason we don't know is that no one has written down a firewall metric. There's no such thing as a firewall metric. And, and therefore, we don't really know how to understand, these holographic entanglement entropy prescriptions are semi-classical prescriptions where you write down a metric and then you try and understand, how minimal surfaces look like there. And because no one has written down a firewall metric, we don't know how to compute minimal surfaces. And so, we can't say much about how this prescription would work. We don't even know if the prescription would necessarily work. Right? So we don't know how minimal surfaces would look, but in fact, it may be that so we don't know the minimal surfaces, but it may be also that the prescription itself runs into trouble, or you need to generalize it, or think about it more carefully, or do something else. So in general, the answer is, if you ask this question, which is if there was a firewall, how would we do this? We don't know the answer to that. But the fact that you see a page curve doesn't tell you that the interior is smooth, and this is an important thing which I think perhaps is not appreciated enough. And in fact, it's one reason why I feel that these last few lectures, these are like important questions about large black holes in ADS, which many things that we discussed previously, which represent an advance in understanding of many other aspects of black holes and evaporating black holes, don't really address these questions. And so I think it's worth thinking again about these questions. So I just wanted to make that clear. If there are any questions about this, I can take this now. Otherwise, we'll go back to our discussion of the eternal black hole. Great. Okay, great. So let me just go back to where we ended last time. In fact, I'll just copy from here. We ended yesterday's lecture on the following note. Okay, we said that sometimes you might have thought, and when these paradoxes were first produced, people did think that these paradoxes hold for like typical pure states in ADS-CFT, but there is some system which we think we understand well, which is the eternal black hole system. So now what we'd like to understand, and this is a subtle argument, so it's worth like going through this slowly and in detail, is that if you believe that you should only use state independent operators, or which is assumption 2 here, if you believe that you should use the same operators in different microstates for the single-sided black hole, and you would therefore believe that there are a set of states which are cousins of the eternal black hole, which are not quite the thermofield double state, but which are the thermofield double state with some time evolution. So they're like very closely related to the first cousins of the thermofield double state. So if you take these first cousins of the thermofield double state, and you believe that it's the same operators that describe the degrees of freedom in the interior of the thermofield state and of these first cousins, and you put in one additional very weak assumption, which is the fact that if you don't have any entanglement at all, if you just take an energy eigenstate on the left and energy eigenstate on the right, then such a state does not have a wormhole that connects them, which is a reasonable assumption. So if you believe the basic duality, if you believe that you should have state independence, which is what led to the paradoxes for the large black holes, and if you believe that disentangled states do not have a wormhole, then we will run into a paradox even for the eternal black hole. So this is to say that these paradoxes that we found for single-sided large black holes are significant paradoxes, and they can't be brushed under the carpet by saying, we'll just think about the eternal black hole when we get confused or something else. And so I think they're paradoxes that we need to think about carefully. So now I'm going to describe this paradox for the eternal black hole. Great. So let's start by taking the eternal black hole, and I'll draw the diagram again. And even though there are two sides to this black hole, we will only keep thinking of an observer who like jumps in from the right-hand side. Okay, so here's my singularity. Here are my horizons. Okay. And I want to consider an observer who jumps in maybe at time t equal to 0. So this is the world line of the observer. Okay. And as the observer jumps in, remember we said, we are interested in physics in some region which straddles the horizon. The observer can make some measurements, maybe the observer carries a detector, but the observer has some experiences, and those experiences are described by taking the eternal black hole state and by measuring in this eternal black hole state, or by considering in this eternal black hole state, some correlators of the natural bulk observables, which, when the bulk is weakly coupled and has propagating fields, are just field degrees of freedom in the bulk. So the observables we are interested in are where you take this thermofield double state and then you look at some observables of this kind, some correlation functions of this kind, and we want to ask where these x1s and x2s are somewhere here. Okay, so they're along the points of this observer falling in, or maybe you have a set of observers who fall in together. But the basic point is that this has to do with observers who fall in from the right, and the fact that the observers fall in from the right is to emphasize that these operators, as we discussed yesterday in a theory of gravity, need to be dressed, and you need to be careful about how exactly the operators are dressed. Here we are talking about operators that are dressed to the right boundary. Okay? So we are talking about the experience of an infalling observer who falls in from the right boundary. Okay, so what can we say about such an observer, or a set of observers who fall in from the right boundary? So one thing we can say, which is that we know that this is an eternal black hole. So it is not a black hole which was formed from collapse, and we see that in the fact that the state on the right is really a mixed state. There's no time in the past when the state becomes something simple, so it really is exactly an eternal state. And what that tells you is that we can translate the entire trajectory in time by tau. By time tau, and the observer should have the same experience. Okay. So, and that's that's kind of it's a pretty weak statement about the duality. It's the statement that there's no preferred origin of time. So there is, by the way, some preference or something you can talk about if you were to excite this eternal black hole with some shock wave on the left, or if you were to do something of this kind, if you were to break the fact that it's an eternal black hole and consider some excited state, then you could create an origin of time with respect to that excitation that you had. But here we are just saying that if you take the original eternal thermofield double state, then there is no origin of time, right? You could say there's no clock in the system that tells you that observers who jump in at t equal to 0 will see a smooth horizon, and observers who jump in later will not. By the way, I should just say something, which is that the Penrose diagram is a little deceptive. You might think that there is less space up here and there's more space up here, but that's actually not the case. In fact, if you think of the world line of an observer who jumps in on this trajectory, the time it takes for this observer to reach the horizon is exactly the same as the time it takes for this observer to reach the horizon. And also the proper time from the horizon to this singularity is exactly the same for this trajectory as it is for this trajectory. So the Penrose diagram is a little misleading. It tends to kind of scrunch up a lot of time up here. But even if you have an observer who jumps in like very, very, very late, and so it's very hard to see on the Penrose diagram, because in drawing the Penrose diagram, you choose an origin of time. That doesn't mean that this observer actually has a different experience from an observer who falls in like at very early times. Okay, so the world lines look very different. An observer who falls in near t equal to minus infinity, it looks like on the Penrose diagram, this is the world line, whereas for an observer here, it looks like the world line is this one. But really, these are related by symmetry, and the experience of these two observers we expect is the same. Now, of course, it could be that maybe the duality itself doesn't make sense, and there is some preferred origin of time, and that's our assumption one. Right? So if the duality makes sense, then in the eternal black hole, there's no origin of time, and therefore we believe this. What does this mean in equations? Okay, so I said a bunch of words. It means the following thing in equations. It means that if I act with e to the I hr tau, okay, I can act, by the way, with let me just write this equation and then it'll be clear. Hr tau, that this is the same as the set of correlators in the original thermofield double state. Okay. I have written here hr tau, but in fact, you could also act with e to the I hl plus hr tau by 2. Okay. And remember, the thermofield double state has a symmetry, which is that it is invariant under the action of HL minus HR. Okay? So whether you write HR or HL plus HR or actually only HL, it doesn't matter. But it's convenient, since we're thinking physically in terms of these observers who fall in from the right boundary, to think in terms of e to the I HR tau. But you could use this symmetry to replace this with a different combination of HL plus HR. Okay? So this is the statement in equations of what we just said, of the physics I just said. The fact that the experience of the observer is invariant in time is in equations tells us that whatever the field observables we have and whatever correlators we have, they should have the property that they should be the same in the thermofield double state. And if you take the whole state and you translate it with e to the I HR tau. Okay. Okay. So now let's just take this equation we have and let's just expand it out. Remember that the thermofield double state itself has the expansion So what I'm going to do now is I'm just going to take this. So let's say we act with e to the I HR tau at minus HR tau. Yeah. So yeah, I hope I kept my signs consistent. So if I just act with e to the minus I HR tau, notice all I do is I get some phases. So earlier I just had e to the minus beta e by 2 times e to the minus I e tau. Times a phase of 1, and now I have got some phases here, and these phases are all that this action does. Okay, great. Now the statement that these correlators are invariant under time translation is really an exact statement. It's not some approximate statement where you're allowed to say that, oh, I think the correlators are invariant under time translation up to exponentially small corrections. And the reason is that, you really have no origin of time in the eternal black hole. It's not that, there is no origin of time from 0 to 10,000, and then beyond that, there's some origin of time. If you have no origin of time, you really have no origin of time. And therefore, we believe that this equation up here should be an exact equation for the eternal black hole. If there is something that's going to break this at exponentially large times or exponentially small times or something like that, it would tell us that we would have to correct the duality in some way. And it's quite hard actually to correct the duality in some way because you'd end up breaking like a pretty basic symmetry. You'd end up having quite a different geometry if you try and insert some shock waves in this geometry, and you'd have to understand that much better. And so in the absence of that, if you believe this is really an exact statement, then you can just take this expression here and work out what these correlators have to be. Okay, so let's do that. So let's just take this and work it out.
Can I ask a question?
Yeah, sure. Yeah.
Very quick question. You said before that this reasoning where you evolve with the right Hamiltonian, you could evolve with the sum of the right and left Hamiltonian, but the geometry is symmetric under the difference of the two Hamiltonians, right? So
correct.
evolution the right and evolution to the
so this is the statement that, yeah, go on.
Yeah, I just wanted to know if statement is still true if you evolve with the sum of the two Hamiltonians.
Yeah, because you see, you can evolve. You can write this way, right? You can write this as think of this expression. This expression is the same as the expression I have on top because this thing in the middle just doesn't do anything, right? This is just one. So this is just the thermofield double state itself.
Okay, makes sense.
But this expression itself is e to the I HL plus HR by tau by 2. So you can always insert like a factor of e to the I HL minus HR tau by 2 multiplied with whatever you like, and you can use such factors to turn this e to the I HR tau into something like this.
Thank you.
Okay, let's. Is there another question? Yeah.
Yes, yeah. So in the first line, you wrote down an equality,
right?
Which is just a time translation symmetry in a sense. So right. It actually does not use the full duality, right? It just uses that the symmetry consideration should be same in both sides.
Yeah, I mean, yeah, this is not a, yeah, it doesn't use the full duality. I'm not sure what the question is, but you're right. You know, we're only using the fact that the experience of an infalling observer is the same, whether you jump in at early times or at late times.
Okay.
Right. Yeah, we're not using, I mean, there are many other details of the duality, which we are not using. We're only using the fact that there's this, there's no natural origin of time only on the right. Of course, if you take the eternal black hole, you act in it with some state, then there will be, but otherwise there is not.
Okay, yeah.
Okay,
I guess I had a question that is connected to this. So you said if we believe the duality, then we have this conclusion. I think it's that initial part, that why if we believe the duality, then we have this.
Well, if you don't believe the duality at all, then I mean, if you don't believe the duality at all, then I mean, if someone says that, you know, the thermofield double state is not the eternal black hole, but it's the eternal black hole with, I don't know, some shock wave here, or somebody says something like that. I don't know, this is not a consistent story, but if somebody says that, then, you know, there would be no time translational symmetry, right? Then it would be the case that, so if someone said the thermofield double state is only dual to something like this, which is clearly very asymmetric and doesn't make sense, but let's say somebody said it, then at least they could get rid of this problem, because now, you know, it's not true that the experience of the infalling observer is the same here and here. You know, here the boost is different and here the boost is different. So if you find some way of, it's pretty hard to do, as you can see, you know, to while preserving the symmetries. But if you find some way of, you know, taking the thermofield double and adding to it something that breaks this time translational symmetry in the geometry, then you would not have this statement. So that's all I meant. I mean, I was not saying anything deeper.
I understand. Thank you.
Okay, great. So okay, so we have this expression now for e to the I HR tau, and let's just take this and let's work out what this is. So we have these insertions. And if you just work out what this is, you will find the following expression. There's some simple algebra. So first you will find some sum over diagonal states. Notice that when you look at diagonal states, in diagonal states, you know, these phase factors don't count at all. So when I mean diagonal states, sorry, all states are I mean states where the energy on the left, you pick up the energy on the left and the same energy on the right. Okay? So I'm just separating this set of terms for which the phase factor from the left and the phase factor from the right cancels out. And then there is another expression, which is a sum of E not equal to E prime, which looks like this. And again has a factor of e to the minus beta, this time e plus e prime over 2. So it looks slightly different. E to the I, e prime minus e tau, and the same thing. Okay. So I just took the expression and I expanded it out. And I have taken this sum that you had in the thermofield double state. Remember, it's a sum over all energies. So you have a sum over E prime here and a sum over E here. And then I broke it up into two parts, one where you took the same energy from the ket and the bra, and one where you took different energies. And here I have a phase, which you see here, and here I have no phase. Okay. Now notice that of these two terms, there is only one term that has any dependence on tau, and that is this term. So the only term that has any dependence on tau is this term. And this term has no dependence on tau. In fact, you could also say the other way around. The only term in this whole expansion which is tau independent is this term, where you pick the diagonal terms, and whereas this term has a clear tau dependence. Okay. So the expression that we had previously that told us that this whole thing had to be invariant under any tau translation tells us that, you know, remember, this is something which is true for arbitrary tau. If this was something that was true for like some range of tau, then you might have said, you know, we have some matrix elements here, and the matrix elements are such that they conspire so that you know, this expression is 0 between tau equal to minus 10 to 10, and it's non-zero after that. But because we have said that this expression is independent of tau for all tau, in fact, it must be the case that this whole term vanishes. So this whole term just cannot contribute, and it must therefore be the case that this set of field insertions that describe the experience of the infalling observer from the right has the property that this just vanishes for E prime not equal to E. And the only term that can contribute is this term. So even though in principle you had these off-diagonal terms, the fact that this is independent of tau tells you that the contribution can only come from the first term on top, and the second term cannot contribute, and it must somehow be, so we don't know how it's going to happen, but our logic is leading us, or our assumptions are leading us to the conclusion that it must somehow be that the observables which describe the experience of the right infalling observer have the property that they don't have any cross terms for E prime not equal to E. Okay, great. So therefore, it must be that the experience of the infalling observer is described by this sum that we have on top. Okay. Now, if you look at this sum, if you look at this sum, then this is the kind of sum that we see many times in statistical mechanics. It's a sum that involves, it's a thermal sum that goes over an infinite number of states. But in this infinite number of states, as we know very well, there is a density of states. The density of states is still e to the s, because remember the left and the right CFTs are being set to the same energy eigenstate. So in a sense, from a statistical point of view, this sum looks a lot like a sum in a single CFT. And the point therefore is that we can replace this entire correlator with a sum of this kind. Okay. It must be that these correlators also correctly describe the experience of the infalling observer using the equivalence of ensembles, where this E tilde is now a typical energy eigenstate. So in making this last equality, I made some errors. There's some errors which are order 1 over square root s. But those errors will not be important. The point is that the experience of the infalling observer, we have now argued, is actually the same as the experience of the infalling observer in a typical energy eigenstate. And the key part about this energy eigenstate pair that you see is that it is disentangled. So this state is a disentangled state. Notice there is no more any sum over e's. We now have really just a disentangled state. And we have using this fact, in the beginning, we had a sum over e's and e prime. So we had all of these cross terms. Then we used the fact that, this correlator had to be independent of tau to argue that those cross terms actually couldn't contribute. And therefore, the experience of this infalling observer must actually be the same as the experience of the infalling observer in a disentangled state. Okay. Now, this by itself, so this is an important part of the logic, but this by itself, is not, it doesn't immediately seem to be a contradiction, because somebody might have said, fine, but a disentangled state, after all, is still like a black hole on both sides, because here E tilde is a typical energy eigenstate. And a typical energy eigenstate, still corresponds, we believe should correspond to a black hole in a single-sided theory. And so maybe, it is the case that the experience of the infalling observer in the thermofield double state is the same as the experience of the infalling observer when you take this disentangled state of two CFTs and you compute the correlators in that. But now, remember, we had a no wormhole in disentangled states assumption. So we have a no wormhole in disentangled states. What does it mean to say that there is no wormhole in disentangled states? What it means to say that there is no wormhole in disentangled states means that nothing from the left should be able to hit the right observer. So this is what it means physically. In a disentangled state. Okay. So it could be that, disentangled states are black holes. But, if they are black holes, then, there is no wormhole between them. Or if there's a wormhole, the wormhole somehow has infinite length. And so this kind of picture we had here in the beginning, where, you could have an observer who goes in and the observer can get hit by something. This is because there's a wormhole and the wormhole has finite length. And so you can send something early enough to hit this observer who goes in. But in a disentangled state, that would not make sense. So if there was no wormhole, that would not make sense. And so it should be the case that, and so in equations, what this means is that if you take a disentangled state, I'll just write E to make the notation simpler. Just remember, E is now a typical energy eigenstate. It should be the case that any unitary action on the left does not change the correlator. Okay, this is in equations, the statement of the no wormhole hypothesis. It's a statement that you act with any unitary on the left-hand side, and it cannot now affect the experience of the infalling observer in the disentangled state. So, maybe it could have, and we know it does affect the experience of the infalling observer in the entangled state. So in the entangled state, the experience of the infalling observer can be affected. But if there's no wormhole in the disentangled state, then you believe that, there should be, this should be true for arbitrary unitaries UL. Okay? Now, the only way this can be true for arbitrary unitaries UL can be if phi x1 and phi xn is an operator in the right CFT. You can check that, otherwise it can't be that it commutes with all unitaries in the left CFT. If there's no wormhole, then that tells us that, this matrix element should be totally unchanged. You can act with whatever unitary you like. You can take the energy eigenstate and turn it into a vacuum, or you can act with some very violent unitary, but it should just not be able to do anything to this, observer on the right. And if that is the case, then that's leading us to the conclusion that phi x1 to xn is an operator in the right CFT. By the way, I should emphasize all of these conclusions are not correct conclusions. They're all conclusions that are leading us to a paradox. So please keep that in mind if you look at it later. This is not the conclusion we have drawn right now is not a valid conclusion. It just is a conclusion we are being led to by the assumptions that we made. But now, if it is, go on. Is there a question? Yeah.
I have a question about the last statement.
Yeah.
In which you wrote that these operators are the right CFT operators. Mm-hmm. But similarly, if we do the same with left boundary and take the observer going from the left boundary, by keeping some of the points which is inside the black hole same, like x ends, for example, then we can argue that this could be a left operator also.
Yeah. But you see, the point is, that's a good question. But you have to be careful about how you dress the operator. So somebody might say that, and this, by the way, is something that you see, you've seen many times. We also discussed when we were discussing entanglement wedges. It might sometimes happen that, the operator at a point doesn't actually mean something. So when we write phi of x1, that is not a meaningful statement by itself. When you write phi of x1, you're actually referring not to a local operator at the point x1, but you're referring to a non-local operator where you have dressed the point x1 in some way. So the usual way of dressing it, physical way of dressing it, is to say you start at some point on the asymptotic boundary and then you shoot a geodesic, and the geodesic reaches some point x1 and then you measure the field there. But in the eternal black hole, there are two ways of dressing points. There is a way of dressing points to the right boundary and there's a way of dressing points to the left boundary. So, if you just evaluate the field at x1, that's an ambiguous thing. And what this, if you were to play the same game for a left infalling observer, what it would tell you is that field operators which are dressed to the left boundary are operators only in the left CFT. So the fact that they have only a coordinate element in common doesn't tell you that they're the same operator. You have to be careful also about the dressing. So both of these are wrong conclusions. It will not be the case that operators dressed to the left in the interior are only operators in the left CFT, and neither is it the case that operators dressed to the right are operators in the right CFT. But you wouldn't just immediately get a paradox by playing this game on the left hand side. I mean, there's a way out, which is that someone would say operators dressed to the left boundary are operators in the left CFT, operators dressed to the right boundary are operators in the right CFT. Okay.
So sorry, if you want to dress the operator with respect to the boundaries, and we have an ambiguity that we can dress it either left boundary or from the right boundary.
Right.
So in the eternal black hole case, I mean, this ambiguity cannot be resolved at least if we stick to this prescription of dressing.
There is always an ambiguity in local operators in gravity. There's always an ambiguity about how you dress the operator. So right now I said to the right CFT, but in principle, that itself does not fix the ambiguity. You have to decide how exactly you dress it to the right CFT. Do you dress it with light-like geodesics or space-like geodesics? Or, do you do a gauge fixing or do you do something else? So there are many ways of dressing operators, and you have to decide what that is. You should just be careful that, phi fx is not a meaningful thing by itself. There's no such thing as a gauge invariant local operator in gravity, as we said many times. And, all operators are non-local in some way, but here we are thinking of operators where we somehow push that non-locality to the right CFT. And this ambiguity is just all, we don't always make it explicit, but it's always there in gravity. And I mean, this is, yeah.
Okay, yeah. Okay, yeah, thanks.
Yeah. Okay, great.
Excuse me, can I ask another quick question?
Yeah, sure, yeah.
When in the previous slide you dropped the sum over the eigenstate, are you using Eigenstate thermalization hypothesis?
No, I'm using the equivalence of ensembles here. So it's weaker than Eigenstate thermalization hypothesis. Actually, I don't even have to use the equivalence of ensembles. We could probably carry through the argument without doing it, but it's easier to do it using the equivalence of ensembles. So it's the fact that, it's a kinematical argument. It's the fact that, you just have a sum over a lot of states, and you expect that in this sum is dominated by a small set of states. So it's the statement that the canonical sum is dominated by the microcanonical sum. The Eigenstate thermalization hypothesis is stronger. It's about the fact that in any energy eigenstate you would see something, but this is not a statement about any energy eigenstate, or it's not even a statement about what form the matrix elements have. I mean, actually, we'll refer to the Eigenstate thermalization hypothesis later, but the equivalence of ensembles is something simpler than that.
So that energy eigenstate cannot be any energy eigenstate. It must be Correct. Some typical. Well, with typical you mean the one that is dominant in the sum.
That's right, exactly. And even then there are like corrections here which I have here. So there are corrections which are like order 1 over square root s corrections. So this equivalence of ensembles is never an exact statement. It's always an up to power law corrections in the entropy statement. So that's why I wrote these corrections. And so those are there. And there's also this typical. These corrections could be much larger for some atypical eigenstates. But here we're considering typical eigenstates. Even then you have a correction, but we will not be worried about that correction.
Sorry, can you just clarify what you mean by typical? You mean since it's which is not suppressed in the sum, I guess must be a low energy eigenstate. It's close to the.
No, it's a high energy eigenstate. It's always high energy. I mean, high energy means of the energy of the black hole. But the point is there are e to the s energy eigenstates, right? And many of them behave very similarly. Like, I mean, if you take like an expectation value of an operator, you have like let's say these are e to the s eigenstates, then a lot of them behave very similarly in that, if you take the expectation value of an operator in one of these energy eigenstates, it's the same as this one. There might be some outliers, there might be outliers, like maybe this one is like a bad energy eigenstate, so maybe it has some special properties. So maybe there's some outliers here, but most energy eigenstates behave the same, and that's why you're able to replace the sum over you're able to replace the sum over states just with often with the typical energy eigenstate. So this is not it's not a statement that all energy eigenstates work. It could be that there are some outliers. It's just a statement that the deviation from one energy eigenstate to another energy eigenstate is not too violent. So that really is the equivalence of ensembles. It's the fact that if you look at energies which are, the spacing between these energies at high near the black hole is like e to the minus s. So the statement is, if you look at something which has energy like n squared and n squared plus e to the minus s, the properties of that, the macroscopic properties in terms of like simple field correlators are similar in those two.
Okay, thank you.
Okay, great. Okay, great. So we've been led to this conclusion that phi x1 to phi xn is an operator in the right CFT. But the paradox after this is obvious. It is the fact that we already know, right, there are no operators, are no purely right operators. So that, with the property that if you just take a single energy eigenstate and you just write down like the right operators, describe a smooth experience. This was the paradox we discussed yesterday. So once again, this is important in that this is a question of typical energy eigenstates. There could be operators which describe a smooth experience for atypical energy eigenstates, but for typical energy eigenstates, we know you cannot find operators in only one CFT which describe a smooth experience. And remember, this was an order 1 paradox. And for instance, yesterday, we described how by smearing this phi r a little bit behind the horizon, a little bit ahead of the horizon, you could extract this correlator of A tilde and A tilde dagger, and how that correlator would have the wrong properties in that, if it was the case that these correlators, the correlator of A tilde and A tilde dagger had the correct occupancy, then you would run into a paradox. We also described another paradox involving this NA operator. But basically, the physical point is very simple. We have reduced the eternal black hole case to a single-sided black hole case. And now, we already know from the paradoxes yesterday that in a single-sided black hole, you do not have operators, or you cannot find like fixed state independent operators which describe the experience of an infalling observer. And that tells you that such operators also cannot exist in the eternal black hole. Okay, so let me just make the logic clear so that the logic is clear. The logic is if the operators work, so I'm using this term work, which means that if the operators have the correct properties that we expect from effective field theory, so that's what work means. Okay, so if the operators work in TFD and its cousins, if this happens, then it means that they must also, the same operators must also work in disentangled states. And here we used the time translation argument. Okay, so this was step 1 of the argument. We use the fact that, if you can find operators that work in a thermofield double state and its cousins, the same operators must work in disentangled states. If the operators work in disentangled states, then the no wormhole hypothesis or no wormhole assumption in disentangled states, this tells you that the same operators must also work in a single CFT. But we already found a paradox with this. So this is yesterday's paradox. So this is the chain of logic. The logic is that, we said, we started with saying that, we have these operators in the thermofield double. We have these cousins of the thermofield double, which is the thermofield double state just time translated, because we believe that, time translation in the eternal black hole shouldn't have any physical difference if you time translate everything. Then, we said, well, therefore, it must be the case that, these operators, whatever they are, must also give the correct effective field theory experience for the infalling observer in disentangled states. But if they work in disentangled states and disentangled states have no wormhole, then in fact, they must just be operators from a single CFT. And we already know we cannot find operators in the single CFT that give us the right experience for an infalling observer from yesterday's paradoxes. So this is the full logic of the paradox. Let me just elaborate a little bit more to explain, this is probably a subtle paradox, so you should think about it, but let me just elaborate this a little bit more. You see, before this paradox was formulated, sometimes people would say the following. Okay? In fact, sometimes in the literature, you will still find the following. So if you find this claim in the literature, you should know that this is not correct. So I'm going to tell you what the incorrect claim is. Sometimes people would say, here is the eternal black hole, and here's how we can expand the field. On the right wedge, so let's call this the right wedge, left wedge, forward wedge, and maybe past wedge. Okay, so right R is for light, L is for left, F is for forward, P is for past. So we could have said, well, we have this field expansion, and the way you expand the field is by taking some modes from the right CFT and by multiplying them with some functions. In fact, this is what's called the Hkl Reconstruction. And it says, you take some modes from the right CFT, you multiply it with some appropriate spacetime functions, you sum over all modes and the Hermitian conjugate. This gives you the expansion of the field or mapping between the field and the right boundary in the right CFT and the right wedge of the thermofield double. In the left wedge, you do something similar. You say, well, phi is A left, times a function, and then you have a Hermitian conjugate. And this is a operator from the right CFT. Right? And this is an operator from the left CFT. And then people would say, well, in the forward wedge, you now have both operators, both from the left CFT and from the right CFT. So here we will write down phi is equal to AR omega into some function G1 into TR omega plus AL omega into G2 of TR omega. Okay. So here is our expansion for the forward wedge. So you take the left operators and the right operators and you write down the sum, and that's our expansion. In fact, if you work in Rindler space, then this is indeed how things do work in Rindler space, in that you have some modes on the right Rindler wedge, on the left Rindler wedge. In the forward wedge, you get modes from the right Rindler wedge and from the left Rindler wedge. Right? So someone might have said, well, here is my expansion of the field operator in the interior, in the forward wedge. And this clearly just works, it doesn't have any problems. And making the statement that this is the expansion is actually equivalent to saying that these A tilde omega operators are just modes from the left CFT. So you can take the operators from the left CFT and take the Fourier transform, and you have to normalize them correctly so that they have canonical commutators. And the statement that this expansion in the forward wedge is given by just AR plus AL is the statement that what we have been calling A tilde, which is the field integrated behind the horizon, is actually the mode from the left CFT. And superficially, it looks like it does work because it is the case that in the thermofield double state, AL omega, AR omega does have the correlator that we want. So this is indeed the correlator that we wanted for A tilde and A. Okay. So if it is the case that, A tilde is AL and A omega is just AR, then, it looks like in the thermofield double state, we have the right correlation functions. But this is not correct because this transformation, this reconstruction does not obey the correct properties if you do time translation. So in particular, if you now take the time translation of this correlation function, and you translate it with e to the I HR tau, then you pick up a phase. You pick up a phase because the right Hamiltonian commutes with AL, but does not commute with AR, right? So the right Hamiltonian is going to exactly commute with AL, but not with AR. And therefore, this will just give you some factor of e to the I omega tau times the original term. And this violates the statement we had that, the thermofield double state should be invariant under, the experience of the infalling observer should be invariant under, under time translations. So if you were to take this expansion seriously, this kind of expansion where you really take AR plus AL, then this would lead you to this conclusion that we have here. And it would actually lead you to the conclusion that e to the I HR tau into psi TFT is a singular state. And that doesn't make any sense just by looking at the geometry. If you time translate something, you should not get a singular state. Just to emphasize once more, this conclusion that we have here, that this is a singular state, if you really had quantum field theory in the bulk and you didn't have, quantum gravity, then in a sense, this would not be an unreasonable conclusion. In fact, you can check that if you take Rindler space and you take Minkowski space and you try and do a translation with the Rindler Hamiltonian, then it would happen that you would get a singularity. But in the case of quantum gravity, that's not the case because these time translations are really just large diffeomorphisms, and they don't actually mess up anything locally near the horizon as they would if you had quantum field theory without gravity. Okay? So just to elaborate, the paradox that we outlined right now is relevant, and it tells us that these kinds of constructions where you just write down AL plus AR are not quite correct, and they need to be fixed. So this is a subtle issue, but it is an important issue, and we will in fact later discuss how to fix this. Okay? Let me just make one more point. If we relax the no wormhole hypothesis or no wormhole in disentangled states hypothesis, then one can construct operators that give us the correct experience for the infalling observer. Okay? Which do have the correct time translation properties. So if you're willing to accept that you do have a wormhole in the disentangled states, then you can get some operators that behave correctly in the thermofield double state and its cousins. This I'm not going to go through in class, but if you'd like to see, these are kind of funny kind of operators. I'm going to refer you to archive 1503.08825. This is a very long paper, so look at page 64. Okay, where these operators are constructed. So that are just some things I said to elaborate on the paradox for the eternal black hole. So we'll discuss the resolution. I should say something actually, just a note of caution. In the review and the lecture notes that are on the archive for this course, I tried to make this argument a little brief, and I think I didn't succeed entirely. I might in fact have made it a little inaccurate or a little confusing. So in fact, if you'd like to see where this argument is done with many of the subtleties discussed, the place this argument was originally discussed was in 1502.06692. And perhaps you should just look directly at this paper rather than looking at the lecture notes for this particular paradox. I will try and fix this, but it may take me a couple of weeks to fix it. So please just try and look at this paper if you'd like to see where this appeared originally in the literature. Okay, so I'm going to stop here we'll discuss other things, but I'm going to stop the discussion of this eternal black hole paradox. I wanted to describe a few other simple paradoxes about large black holes, and then we'll come back to these paradoxes. So this is a set of paradoxes that I think are, conceptually significant paradoxes which apply to large black holes in ADS and also to the eternal black hole. I want to spend the last 20 or 30 minutes discussing another set of paradoxes that apply to large black holes, but are not, I think, conceptually very deep, but should be mentioned. And so I will do that in the last 30 minutes. But if there are any questions before that about this paradox, I can take them now. Okay. So if you have questions in the next lecture, we can take them there as well. Please do think about this paradox. It is, as far as we know this is a correct argument, but it's a subtle argument, and as I said, it's not appreciated. I think sufficiently that there is an issue also with the eternal black hole, and this issue of firewalls or state dependence or state independence is something that applies also to this very well or what we think is a very well understood and clean setup as well. Okay, great. So now I'm going to talk about what is sometimes called I don't know, the easy information paradox, or some very simple set of paradoxes. Okay. So these paradoxes have to do with So I want to spend some time just to mention, since we have some time left, some simple paradoxes. In fact, these paradoxes were discussed, and even though they're simple, they're amenable to computations. And so they're interesting because usually when we have these discussions, we have discussions and there are arguments about existence proofs or some other arguments about results about how information should come out. But in this setup, there are actually interesting concrete computations one can do. But I think we understand pretty well how these paradoxes should be resolved. But since they're discussed in the literature, I thought I should mention them. So one paradox is a paradox about 2-point functions. And all these paradoxes have to do with exponentially suppressed effects. Okay. So these are all paradoxes about exponentially suppressed effects. As opposed to that, let me point out that the paradox I described previously was an order 1 paradox, because this negative occupancy paradox and so on are all order 1 paradoxes. And the paradoxes I'm now going to describe are paradoxes which have to do with exponentially suppressed effects. So here is a paradox which involves 2-point functions. Okay. So let's take, we can take a pure state in a CFT, or we can take a thermofield double state. But let's take a pure state just for simplicity, and consider some 2-point function in this thermal state, okay, where this is a light boundary operator. Okay. So it's dual to some field. Okay, we don't have to take such an operator. You could take something more complicated, but this is the simplest case to consider. Okay. Now, just for simplicity, I'm going to take this 2-point function and I'm going to set its 1-point function to 0, which is the statement that this is 0. We don't have to make this the statement, but I'm going to set it to 0 so that the expectation value of this operator in an energy eigenstate, which is relevant for the black hole, is 0, and it's just exactly 0. I'm just going to subtract off the 1-point function. If you like, you can just redo this paradox while subtracting off the expectation value, but just for notational simplicity, I'm going to make this assumption. Okay. So now you can ask, how does this 2-point function behave at large times? Okay. So the question is, what happens at large t? Okay, so what happens at large t? So of course, one can do a bulk computation to see what happens at large t. And in the bulk, we know what happens at large t. If you take a 2-point function and you hit the geometry, then let's say you have a black hole and you hit the geometry. So that's what this first O can be. You hit the geometry at time 0, and then you make a measurement at time t. So what happens to this geometry that you hit? Well, the geometry rings. And then the ringing or the effects in the geometry tend to die off, and they tend to die off exponentially because those are the quasi-normal modes of the black hole. Okay? That's because, if you throw some energy, then from a classical perspective, this energy starts to decay and, things start to fall into the black hole. So if you hit the geometry at some point and you go to a later time and you try and measure how much energy is left, then that energy is much smaller than the energy that you inserted initially. And in fact, it dies off as e to the minus kt from a naive bulk computation. Okay, so this and this k frequency is controlled by the quasi-normal modes, so you can compute for a given geometry what this leading exponent will be. But the main point is that this 2-point function dies off exponentially at late times. So maybe initially there's some complicated dynamics, but then at late times you start getting a decay, and then this decay is exponential. But now, what do we expect from the CFT for this 2-point function at late times? So what about the CFT? So in the CFT, we are computing here this 2-point function. And one way to compute the 2-point function is to insert a set of energy eigenstates in the middle. So I've inserted a set of energy eigenstates in the middle. And now that I've inserted this set of energy eigenstates, I can ask, what is the typical magnitude of this contribution that I get? Okay. So now, one way to think about this magnitude of this contribution is to use some kind of, is to use basically some kind of random phase approximation. And so what you have here is a contribution from e to the s states That's the contribution that you see in the middle, because the sum over E runs over E to the S states. But on the other hand, each contribution is expected to be a small contribution. Okay? And each of these contributions is expected to be of size e to the minus s. Sorry, to be of size e to the minus s by 2. So in doing this, we invoked, earlier there was a discussion of the eigenstate thermalization hypothesis. So if you were to invoke the eigenstate thermalization hypothesis, that's what the eigenstate thermalization hypothesis would tell you. But really, it's something which is pretty simple to understand. It's the statement that, if you take the magnitude or you take the matrix elements of an operator between two energy eigenstates. Okay? So you take like E of O and some operator. Then you tend to get some matrix elements, and you get some matrix elements which contribute when you have diagonal terms. So this is the eigenstate thermalization hypothesis. And then you get some matrix elements which are just random phases which contribute when E prime is not equal to E. Okay? Now, why is this the right expectation to have? This just comes by taking a typical matrix and by looking at the elements of the matrix in some random basis. So, if you just take some matrix and you just, you have some matrix in a big Hilbert space, which is of size e to the s, and you just do some basis transformation, and you try and, this matrix has some trace that you understand, and you look at what is the expected size of the entries of this matrix, then this is what you would find. So, this is, it goes by some fancy terms, but it's really something pretty simple, where this is some random phase. So if you were to apply this hypothesis here, you see, you would get psi itself is some linear combination of different energy eigenstates. And you see here that, there is one term where you get if you were to expand out this psi, where you would get this diagonal term, which is E into O into E itself. But you expect that the overlap of psi with any given energy eigenstate is itself of size e to the minus s by 2. Okay? And that's because you expect that psi is some typical superposition of different energy eigenstates. And the same here. Okay? And therefore, you see that all the terms that contribute to this matrix element are of size e to the minus s by 2. And that's why you expect that this entire matrix element, so when you say each contribution, I mean you expect that this entire matrix element is of size e to the minus s by 2. Okay. So psi of t e is order e to the minus s by 2. Okay. Now you have two such matrix elements. So you get e to the minus s because you have this one and you have this one. So you get e to the minus s. But if t was a small number, so if t was a small number, then these e to the minus s terms, which are summing over e to the s terms, would be correlated with each other. They would not be uncorrelated with each other. And therefore, you would have an e to the minus s from the sizes, you would have an e to the s from the sum, and you would expect to get a correlation function which is of order 1. But at late times, you expect that this matrix element is uncorrelated with this matrix element. And indeed, if you go to late enough times, you would expect that. If that is the case, then you have a sum over e to the s terms, each of which is of size e to the minus s. And therefore, of size e to the minus s, but with random phases. And that whole expression you expect will be of order e to the minus s by 2. Okay. So just by this very simple random phase counting argument, we end up with the conclusion that this expression in the CFT is expected to be of order e to the minus s by 2 at late enough times. Okay, how large does T have to be? T has to be large enough that you tend to lose correlations. And when we say order e to the minus s by 2, that doesn't mean that this is the value for all times. Our approximation was pretty crude. There are of course fluctuations. There might even be Poincare recurrence. So there would be some times when this correlator was much larger than order e to the minus s by 2. There would be some times when it would be much smaller, when maybe it becomes very close to 0. But this is the typical average value that you expect for large enough times. This is the size of the typical average value that you expect. So you see that this contradicts the bulk computation when T is of order S. Because when T is of order S, you start finding that the bulk computation just keeps decaying and decaying forever, whereas the boundary computation has a fat tail. So sometimes, people say that this is a version of the information paradox, and in a sense it is, that you expect that from unitarity, you would expect to see these contributions which have a fat tail, which have these order e to the minus s by 2 contributions at late times, whereas in the bulk you find that you just keep decaying and keep losing information. And so how do you resolve that? So of course, this is a non-perturbative effect, and it is sometimes noticed that this kind, and in fact, when this paradox was first discussed, in fact, by Maldacena in the original paper on the eternal black hole, the proposal was that, there is, remember, we're talking about a single black hole. We're talking about a classical geometry that corresponds to a big black hole. But there is always another saddle point, which corresponds to some, which is the gas of gravitons, which we usually neglect because once we are at a temperature which is above the Hawking-Page transition temperature, we say, oh, we don't have to care about the gas of gravitons. It's the black hole that dominates. But if we start asking questions at this level of accuracy, at this order e⁻s/2 level of accuracy, then we may need to worry about other saddles as well. From other saddles. Now, there's been some discussion in the literature about whether this other saddle is sufficient to give this contribution, or how you should get it. And it's a detailed question which one needs to ask. But in principle, if you could simulate, for instance, n equal to 4 super Yang-Mills, you could take an excited state and you could compute the correlation function, and you'd be guaranteed to get that at late times you would have this behavior, this order e⁻s/2, because that just follows from some random phase and very, very simple assumptions. And then if you could also do the bulk computation, you could do the bulk computation and you could see how the fat tail emerges. Okay. In fact, there's something similar where this has actually been done, or something similar to what I just described has been done. And that is actually has to do with the thermofield double states that we just discussed. We discussed just some time earlier these thermofield double states. So one could ask the following question. What is the overlap of such a state with the original thermofield double state? Okay, so let's say you take such a state, you look at the overlap with the original state, how much is that? And if you were to expand this out, you would find that this looks like e⁻e tau, e⁻β e, and 1 over z of beta. So of course, if tau is 0, this overlap would just be 1. But for large tau, this overlap would start receiving various contributions. And you can check that you can write this entire thing on top as z of beta plus I tau divided by z of beta. So this is sometimes called the spectral form factor nowadays. But what it is really just the overlap of the time shifted thermofield double state with the original thermofield double state. Okay, so it's a z of beta plus I tau by z of beta. If you just are at very short times, for very short times, you can compute what you expect this to be, and you will find that, let's call this psi tau, that this has some form which is e⁻τ square c by beta square, where c is the specific heat of the black hole. But then at late times, in some cases like the SY, okay, let me just say one more thing. For long t, for very large t, you repeat the same argument that I gave you previously. Remember that you have these e⁻s, effectively to this partition function at a given temperature beta, you get e⁻s contributions. But once tau becomes large, these contributions are all contributing with random phases. And therefore, you have a set of e⁻s contributions with random phases. So that gives you something which is suppressed by that's e⁻s/2. Whereas in the denominator, you have something that's the full e⁻s. And therefore, for very large times, you expect this to be of order e⁻s/2. In fact, for times in between this very short time and this large time, there is a rich structure that one can compute. There's this ramp and this plateau, and there's a rich structure that one gets by studying this, which one can do in matrix models and the SYK model as well. Okay? So even here, you could have done the bulk computation. The bulk computation would suggest that this answer that you get for short tau just keeps decaying forever. You just have something that just keeps decaying forever. And then from unitarity already that you should have some contribution at large tau. You should have a fat tail. In fact, there's a more intricate structure that appears before this eventual fat tail, which is already of interest. Okay? So these are again examples of how in some cases, if you take the bulk contribution and you are not careful about these exponentially suppressed terms, you might end up with what you think are paradoxes. In a sense, this is similar to the paradox that Hawking outlined right at the beginning, where he said that, we compute these 2-point functions, we find they're thermal, and that tells us that the state is not pure, it's a mixed state. But, as we saw in the beginning, they're exponentially small corrections, which could easily fix that. And here we see very directly that there are 2-point functions we are computing, and the 2-point functions, can have exponentially small corrections, and you need to be careful about them. So these are, as I said, conceptually not very difficult paradoxes, but they are paradoxes that arise for large black holes, and which are interesting because, these are situations where you can actually compute and see how this behavior goes over to this behavior. Okay. So now I want to discuss one last paradox, which is sometimes called the bags of gold paradox. Actually, we will not discuss the full bags of gold paradox. I'm going to discuss a simplified version of the bags of gold paradox. Sorry, maybe I should ask before that. Are there any questions about this part? Okay. So this I can believe is simple enough that there are no questions. So let me ask the last part, which is about the bags of gold paradox. Let me go on to the last part of what I want to say today. So let me remind you of a feature of the eternal black hole geometry. Actually, this is also a feature of the single-sided black hole, but it becomes more acute for the eternal black hole because you can really compute things there. Okay. So here are our horizons. That's interesting. Okay, and let me remind you that something we discussed when we were also discussing these Hartmann-Maldacena kind of surfaces is that if you were to compute the volume of maximal volume slices, which are anchored at time t, then you would find that the volume of these slices grows like time t for large t. This is just a geometric fact about the black hole. But now, if you start thinking about this geometric fact a little bit more, you can easily run into a puzzle. And this puzzle, as I said, is related to an older paradox called the bags of gold paradox. And the puzzle you could run into is the following. Now, you could say, I have this growing volume in the interior of the black hole. This volume is growing without bound. And as I said, I've drawn these slices in the eternal black hole, but you can similarly draw nice slices in the evaporating black hole as well, just in a large black hole as well, and also in the evaporating black hole. But if you just take a large black hole which doesn't evaporate, it's simplest to draw these nice slices that again tend to stretch and stretch and stretch without limit, as you see the slices doing here. Now, somebody could have said, well, we have these slices which are stretching without limit. Let me now try and create some excitations on these slices. So I can think of a quantum field theory state where I have some excitations. So this is the eternal black hole, but now I can think of an eternal black hole with some excitations sitting inside. If you like, I can remove some energy from the black hole in the background so that the total energy of the system is the same. And you can see that because the slices become longer and longer, I can keep these excitations well separated, and I can put a lot of them. So I can put a lot of excitations, and I can separate the excitations without any trouble. And the reason for that is that the volume of these slices is becoming very, very large. So if I were to treat if you put excitations and count the entropy naively in the dilute gas limit of a dilute gas, we would find that the volume of a gas always grows, the entropy of a gas always grows like the volume within which the gas is sitting, right? We are taught that the entropy of the gas is an extensive quantity. So we would find that the entropy of the gas grows like T for large T. So in particular, if you take T to be large enough, for large enough T, the entropy of the gas has become larger. It can even become much larger than the entropy of the black hole itself. And that's clearly a puzzle, because it suggests that, you have this black hole and you thought you were counting all of these microstates of the black hole. But now you're finding in some sense that, this black hole can support many more microstates than you thought it could support, because it can have all of these huge excitations which are sitting inside. And, if you count the entropy of all of these excitations, you get an entropy that's much larger than the black hole entropy. Now, sometimes people say that, fine, maybe you do, but maybe you can't really create these states while starting with, some smooth initial data. And so maybe you have all of these states which you can write down at late times, but they don't really exist in the theory. Remember also when we discussed this holography of information, it was important for us to restrict to states that could be formed by acting on the vacuum with boundary excitations. And so somebody could say, that is when the boundary knows about what's happening in the bulk. And maybe these kinds of states, you can't form because you can't really act with boundary excitations. But for this particular case, where you have this dilute gas, it's not hard to actually create these states by acting with the boundary. And the way you create these states is actually just by sending in a set of shock waves from the boundary at early enough times. So if you just act with a set of, you take the eternal black hole and you act with a set of shock waves at various times, so let's call this tau n, then you would create a state which looks like in the dilute gas approximation, it has a large number of excitations at late times. So the point is that if you think of this kind of a state with lots of unitaries acting on the thermofield double state, then this state does look like it has a lot of excitations on the nice slice. And the fact that you have, you have this dilute gas limit is the fact that you can separate these unitaries by large times. Okay? So we can separate tau I minus tau j by, we can separate tau I and tau j. So it just means we have these tau 1s to tau n's, and we can just separate them. And so we can ensure that the distance in time on the boundary from where these excitations were sent is large. And that, if you just follow some simple semi-classical reasoning, would lead you to some set of excitations whose distance on these late time slices is large. And that just corresponds to this time, time separation on the boundary. So here we seem to have an example of a situation where we are being able to explicitly create this set of excitations in the bulk, which seems to be violating the Bekenstein-Hawking bound. And as I said, this is related to these older paradoxes where people thought of these exotic solutions, which looked like bags of gold, which again, could look like they could support like a large amount of entropy. And that looked like it was in contradiction with the Bekenstein-Hawking bound. But here, in fact, the resolution to the puzzle is quite clear. And it once more has to do with exponentially small effects. And it has to do with the fact that, we think that if we separate, tau 1 minus tau 2, like by a very large amount compared to the ADS radius, then we think that we should be able to treat like the excitation at tau 1 and the excitation at tau 2 just independently. And so we should be able to think of a dilute gas of such excitations. But in fact, that is not the case, because if you compute the inner product, however much you separate the excitations, it saturates at order e to the minus s for tau 1 minus tau 2 being much, much larger than 1. So in fact, these excitations that from a classical perspective, you think by separating long enough, or by separating by a large enough amount on the nice slice, by exploiting the volume of the late time nice slice, you can make them almost exactly independent, and therefore you can treat them in a dilute gas approximation. You find that when you keep track of these fat tails in the inner product that we just described, these excitations are not independent, and in fact they have some non-zero overlap, and that non-zero overlap is precisely of order e to the minus s. And so counting a dilute gas of such excitations is overcounting. It's overcounting because these states are not quite orthogonal. And you might have thought from the classical perspective, or from a naive bulk perspective, that you could make these states as orthogonal as you like by separating them long enough in time. But you find that that's not the case. You need to keep track of these exponentially small effects, and these states in fact are not orthogonal. And if you don't keep track of this lack of orthogonality, then you would end up with an entropy that's too large. But that's just telling you that in fact you're counting states which are not orthogonal, and so you're not counting the entropy correctly. This doesn't completely resolve this bags of gold paradox, because there are other kinds of configurations one can look at. But in some limit, it tells you that one resolution to these bags of gold types of paradoxes again has to do with exponentially small effects in the inner product, which is now a theme that we've seen occurring a few times. Okay, so this actually brings me to the end of the discussion on paradoxes for large black holes. We're also just in time. Next time, we will discuss a resolution to these paradoxes for large black holes, not these exponentially suppressed paradoxes involving exponentially suppressed terms, but the earlier paradoxes that we described. So we'll describe a resolution to these paradoxes using something called state dependence and a construction of the interior of these large black holes. And then we'll discuss puzzles and critiques of state dependence before we conclude this part. So I think I'll stop here because we're out of time, and we can take questions if there are any.
Suvrat?
Yeah.
In these bags of gold paradox, the entropy of the gas you said is like proportional to volume, but since it's a theory of gravity, why would anyone even start with saying it's proportional to volume rather than being bounded by the area?
Yeah, you're right. But somebody, yeah, good. So somebody might say, look, I can explicitly write down these configurations, and I have this huge volume which is sitting in the gas, and so somebody would come and say to you, you tell me that the entropy is bounded by the area, right? So you say that the entropy is bounded by the area. Very good. I don't believe you. And look, here's how I don't believe you. Look, I can write down all of these configurations which have all of these states, which have all these excitations, as you see here. And here are these excitations. I can write them down explicitly. They are orthogonal. I computed the inner product. I found it was orthogonal. Look, here are all these states. So I don't believe your statement about the entropy being bounded by the area. And the answer, of course, is that you didn't compute the inner product correctly. You computed some inner product. You forgot about this fat tail, and so you counted a lot of states which were not quite orthogonal. You counted states which were not orthogonal, and that's what saves you. That's what tells you that, look, the entropy is actually proportional to the area here, and it's not proportional to this volume that's sitting inside here. But the point is that because you have these volumes that can stretch and that are sitting inside a bounded area, right? Now, usually, if you count the entropy of a gas like in this room, you will not end up violating the Bekenstein-Hawking bound, because you can't just explicitly write down a lot of states where you just have a dilute gas and the area of the room just stays what it is. You will not be able to do that, right? You'll not be able to make the volume increase without bound while keeping the area of the room fixed. But inside the black hole, you do have this funny geometric configuration where the volume of these slices can stretch by a huge amount, which you can't do without black holes. And so somebody might have said, I don't believe your area bound. Look, here are all these configurations. And the answer is, you made a mistake because you counted a lot of non-orthogonal configurations. Does that answer the question?
Okay. And and also, do you mean V is proportional to T, or dV by dt is proportional to T?
Oh, thank you. V is proportional to T. dV. Oh, thank you. V is proportional to T. Not dV by dt is proportional to T. Yeah, dV by dt becomes a constant at late times. Thank you. Thank you for the correction. Yeah.
Thank you.
Are there any other questions?
Yeah, I have a long one, but I'm just waiting if anyone else wants to ask.
Okay, sure. Yeah. Yeah, maybe you can go ahead.
Okay, I just want to understand more about the TFD and the eternal black hole thing.
Sure. Yeah.
Is the following thing right? Let's say, so I have these two CFTs, and for each of those CFTs, I would have an algebra of observables for the left and the right CFTs. And since I have these two things, I can also consider elements like AL into AR, where AL belongs to the algebra of the left side and AR belongs to the algebra of right side. And I can also consider such products and such sums. And then what I do is given all states that I can put in this tensor product Hilbert space, I will look for those elements of the right those elements which has some products in. Okay, so I'll look at those elements in which has some correlations between AL and AR. Like, for example,
so
I'm
thinking
thinking
of
of some
state?
operators. No, like let's say, for example, I have an entangled state, and then if I look at the right wedge, which is outside the black hole, an operator over there will which is in the bulk will be represented by some operators, one purely on the algebra of observables of right hand side of the right CFT.
Right. Correct.
Now, those, if I calculate the correlation functions, or like the correlators between those operators and any operator from the left algebra, I would always get 0. But there would also be some elements in the right algebra
no, that's not true.
whose
If you compute the
correlators with
correlation,
some elements in the left algebra will not be
correct. So in fact, in general, because the state is entangled, correlators of right and left will not be 0. Because there's some entanglement. So correlation functions
but
between
for
right
some,
and left are not.
Yes. No, I'm thinking of like for those kinds of special kinds of operators for which the correlation functions are not 0. I'm thinking of them to be living inside the black hole. And for those combinations of operators for which the correlation is always 0, I'm thinking of them to be living outside the black hole. Is it right?
No, I don't think that's the case, because let's say you take an operator here and you draw this line through its bifurcation point. So this is like OR of T, and this is OL of minus T. This correlator is not 0 in the thermofield double state. So this correlator is not. So these operators are explicitly living outside, and that they're living clearly on two sides. One is living on one boundary, the other is living on the other boundary. So you have correlators between the two boundary theories. This is the fact that correlators are non-zero is like the EPR state. If you take an EPR state, you measure the spin on one side, the spin on the other side. The spin has some correlation. So there's some correlation between the spin on one side and the spin on the other side. So you can have some correlations, and there will be correlations between operators in the CFT as they have to be. So even from the bulk point of view, these are like just simple operators pushed close to the boundary, and they will be simple correlators. What is true is that from the bulk point of view, those operators in the interior of the black hole, are written as sums of right and left operators, which is of course the opposite of the wrong conclusion we reached today. But it's true that if you try and write down the bulk operators in the right wedge, those are like right CFT operators. Bulk operators in the left wedge are left CFT operators, and bulk operators in the forward wedge are sums of right and left CFT operators. But if you're just talking about correlation functions, then those are non-zero even for operators outside the black hole.
Okay. And one more question is, so we initially, when we a few lectures ago, when we had this this ADS in with one boundary, and we had a Cauchy slice on ADS, and we thought of all the operators on that Cauchy slice is actually belonging to that A epsilon on the boundary. So I want to think of something similar to that over here. So can I think of it in the following way? If I draw a Cauchy slice which goes through the bifurcation surface, and I take the part of the Cauchy slice that is on the right wedge, all the operators on that Cauchy slice belongs to the algebra of observables on that point in which it ends on the right boundary. Correct?
Yes, you could think of it that way.
Of it like that, right?
Yeah. You could think of it that way. If you take if you take a slice that runs right through the go on.
Okay, and if I also take a Cauchy slice which goes through the black hole, not through the bifurcation surface, but a bit above, and then again the part of the Cauchy slice which is only on the right wedge, the operators over there will belong to only the algebra of observables on the right side. Similarly for the left side, but the part of the Cauchy slice which is inside the black hole, the operators over there would belong to this bigger algebra which is obtained by taking products and sums of these two small algebras of left and right.
Exactly. That's right. Exactly.
Okay.
Yeah. Absolutely. Yeah.
All right. Okay. Thank you.
Yeah.
Sorry, I also have a question.
Yeah.
So in the case that we add these bath regions, we apparently need the island to resolve this bag of gold paradoxes in that situation, right?
Yes.
So why is it why these sorts of resolutions that you talked about in this case does not work for that?
No, they do work actually. They do work. So I should have said this more clearly. This fact that this S gas goes like T, this is, remember in the island, there was this contribution that was coming from the Hartmann-Maldacena surface, which was coming from, it was this linearly growing contribution. It's precisely this contribution. It's the fact that if you do some wrong computation of the entropy by using some, by neglecting these gravitational constraints and by neglecting all of these inner products, then you will get something which grows linearly. I realize I didn't mention that at all. I forgot to mention it. Indeed, this paradox is precisely the same as the paradox we got while we were looking at the islands, and it is this growth is the same growth, which indeed, as we saw when we looked at islands, had to be cut off. You see, when you do the holographic the computation, you find that the entropy is correct. This is here you're trying to ask why it is that if you make this mistake of trying to count these configurations, which would have led you to this answer, what is the mistake you made in this? If you just use the holographic prescription, you just get the right answer, right? You'll find that the entropy is it is what the Bekenstein-Hawking entropy is. But the question is, someone could say, what is the mistake I'm making? Or is it that you're not counting these configurations that I'm talking about? Or if you are counting them, what is the mistake I'm making? And here we are trying to give a slightly more detailed answer. We are trying to say the mistake that someone who is counting these configurations is making is that that person is not being careful about the inner product. And there are these exponentially small terms in the inner product. Once you keep track of those exponentially small terms, then the answer is very simple. The entropy is S. It is what you expected. And that's, it's because the corrections are also of size e to the minus S. And so, once you keep track of them, you get back the right entropy. But that's the answer. But here we are just trying to ask, what is the mistake that somebody who counted this dilute gas made? So, yeah. And that, so it's not you're right, it's the same, it's a related or very closely related paradox. And here we're just looking at it from a different angle. And does that answer the question? Yeah.